So summarizing, we have two equations, a prediction equation and a correction equation. Our prediction basically takes two components. The estimate of our previous step, that is our belief about x after time t minus 1 was done. And then we have a dynamics model, right? And the way of thinking about this is the likelihood, the probability that x could be at some specific point. Well, it's the sum, or the integral, of getting to that point from any point that it might have been before, integrated over the likelihood that you were at those points before. This is a lot easier to see when we do the particle filtering where we make things discrete. But for the probabilistically inclined for you, if you look at that, you realize, remember we talked about marginalizing. What we're doing is we're saying all of the possible places we might have been before, what is the likelihood of it getting to some particular spot? And we have to weight that by all of the probabilities of having been at that point before. That's the likelihood of being at that next spot. And then you go to the next spot, and the next spot. That's the probability. That's your prior belief of your prediction about the places you might end up. P of xt given the measurements up until now. We don't have the measurement yet. Once we get a measurement, we can do a correction, right? And our correction we use doing Bayes' rule, right? We have the predicted value from before. That's the quantity we just talked about producing. And then we have an observation model. This observation model says, well, if you really were at some particular point, what's the likelihood of getting the measurement you just saw? And by using Bayes' rule, we use that to turn that into a prediction of xt given everything we saw, including, that's why it's in red, the new measurement. And then, like I said, on the bottom here is just the normalization.